Our first speaker here, I'll get right into it because she has a class to teach. She's virtual, Jana Levison from University of Guelph, Morwick 360. Our topic today is nutrients. And if anyone in the audience has ideas for future panels, please speak to me afterwards. I seem to coordinate these. But this is also my last year being officially on the committee since I'm retiring from TRCA in November. So I hope to be here next February, but I can't be the Conservation Authority representative. So without further ado, I'd like to introduce Jana Levison. She's an associate professor in the College of Engineering. Jana.
Okay, thanks for the intro, Don, and congratulations on your upcoming retirement. That's really exciting. So a lot of my research focuses on the interactions of agriculture and rural life with groundwater quality and quantity. So I'm going to touch on that a little bit today. First, I just wanted to highlight a study that a postdoc of mine and some other students have done that's a literature review. So it's a quantitative literature review. They used a text mining algorithm for quantitative analysis. They looked at 800 papers initially, and then through some screening that went down to 516. But they were looking at nutrient dynamics in surface water and groundwater. So looking at topics that have been popular in the past, and then they tried to identify some gaps. So some of the topics they identified are fairly obvious things like nitrate transporting in groundwater has been studied a lot. Phosphorus transport in surface water has been studied a lot. But perhaps more importantly, the gaps that they identified were that we need to do more integrated modeling of groundwater surface water interactions in terms of nutrient transport and nutrient dynamics. The effect of climate change on nutrient transport could use some additional study, as well as better understanding how crops themselves are impacting nutrient transport in groundwater systems and surface water systems. And they identified also that machine learning is an area for development and an area that we can look at in a lot more detail moving forward to help us perhaps understand some new connections. And they also noted that in-stream sediment and nutrient transport in fluvial environments, so say phosphorus sorbed onto sediments, for example, could be studied some more. So I just wanted to touch quickly on a few studies that we've been doing recently that kind of are using different approaches and looking in different areas. So this first one is about 50 kilometers south of where all of you in Waterloo are today in the Grand River watershed, specifically the Lower Whiteman's Creek sub-watershed. In the Norfolk Sand Plain, a very sandy and shallow aquifer system. So Christina Zuner, she's a PhD student, and she's actually presenting about her project on Thursday, so you can find out a few more details then. But she's looking at nitrate transport at various temporal and spatial scales, so using different field techniques to try to better understand storm events specifically and what's happening to nitrate transport during that time, and then also looking at more of a broader sub-watershed scale study of the dynamics of nitrate as well. So one interesting finding so far is that she's found that a lot of there's a lot of nitrate in the tributaries, and there's groundwater discharging with nitrate into those tributaries, which seem to be contributing a lot of the nutrients to the main creek in the area. Secondly, this is a bit of an older study that was done a few years ago now, but a PhD student, Shoaib Salim, he was looking at the impacts of future climate and land use changes on groundwater nitrate. And so this is moving just a bit further south from that previous study that I just mentioned towards Lake Erie in the Lynn River watershed, part of Long Point region. And so Shoaib was looking at he did integrated modeling, and he wanted to look at different land use change scenarios and so in terms of crops, and then different climate change scenarios to force the model to see what the groundwater nitrate would be in the future. So there is a lot of uncertainty with this modeling, but it was a bit of a good news story in terms of thinking about the nitrate in the area. So Shoaib did find that there's a significant reduction in nitrate in the future for the climate change scenarios that he tested, as well as the 3 land use scenarios. So we looked at continuous corn as our worst case scenario, corn soybean rotation, which was the kind of the status quo of what was happening at the time. And then our best management practice scenario was looking at a corn, soybean, winter wheat, red clover as a green manure rotation. And he did find that there was a significant reduction in the nitrate concentrations in the groundwater if that best management practice scenario was adopted, which was a good result. And then the worst case scenario, if we go and plant corn or other crops that require a lot of nutrient application, and then combine that with perhaps extreme climate scenarios in the future, the groundwater has more risk of being contaminated. Next, this is moving more to a clay plain setting. So instead of Lake Erie Basin, moving over towards Lake Huron, about 100 kilometers west of people who are in Waterloo today, in the Upper Park Hill watershed, which is under the jurisdiction of the Sauble Bayfield Conservation Authority. And so we've done a lot of different studies there, but I just wanted to highlight one by Sarah Rickson, a PhD student. So she was looking at subsurface influences on nutrient concentrations and loading in this clay-dominated system. And so she was looking at water quality, water quantity, and also was looking at stable isotopes of water and doing a watershed scale study as well as an edge of field study to understand the dynamics between the groundwater, the soil water, the stream water, and the tile water. This is a very heavily tiled system and very heavily agricultural dominated system. And so some interesting findings from this were that the nutrients in the surface water were elevated during the growing season, yet the loading of the nutrients was much greater during the non-growing season. And the groundwater contributions and the other subsurface contributions were most significant in the non-growing season as well, which was interesting. Next, this is a study that is ongoing this is in the Lake Huron Basin, and Lauren Mulkerns is a master's student who has a poster here today if you get a chance to talk to her at the end of the day. So we're working at the Huron View Demonstration Farm, which is in Clinton, Ontario, and we're aiming to better understand how groundwater and tiles interact in terms of both water quantity and quality, and using a hydrogeological characterization approach for this. So looking deeper than just the first couple of meters in the system. So looking at nitrate quality, phosphorus concentrations in the tile water, in the shallow groundwater, and the deeper groundwater, and also looking at the water budget with some numerical modeling that Lauren is going to be doing. And so it's an interesting site because there's contour tile that has control gates that you can stop the water from flowing through the tiles. And then there's pattern tile. And there's also a field that has no tile drains. So we'll have more results from this study in the upcoming years. Lastly, I just wanted to quickly touch on some machine learning and approaches for using machine learning to predict nutrients in groundwater and surface water. So a postdoc I'm working with, Ahmed El-Sayed, has been doing this, and he's looking at a lot of seeing which machine learning models are the most accurate and doing a lot of tests on that. So I think it is a very promising and, of course, upcoming area that's taking over all different areas and sectors of our lives, but it's something that we can use as an interesting tool to help perhaps gain some new insights about nutrient transport. So just in summary, there's a lot of different approaches we can use to address this issue, but really field and monitoring data that's long-term and high resolution is really critical so we can do the predictive modeling and machine learning approaches. A lot of people contributed to the work that I'm touching on quickly here, so thank you to everyone, especially all the students. And that's it. As Dawn mentioned, I have to teach at 4 o'clock, so I'm gonna have to leave in a few minutes. So I apologize I'm not there in person and that I'm not there to answer questions, but please feel free to email me if you have any questions. Thank you.
We had a previous talk today about the effect of greenhouses around Point Pelee. That's an area I go to typically every year for my birding expeditions. I've seen those greenhouses blossom over the years. And it kind of surprised me that it didn't seem to have a lot of an effect. Are you seeing in any of this research levels? I will say that I dealt with one project up in North Bay a long time ago where we had 200 milligrams per liter nitrate in the ground from a greenhouse. So are you aware of any?
Yeah, good question. I haven't been doing any work in the areas of greenhouses, but just in the study sites that we have been looking at, the nutrient concentrations are quite high in the groundwater, especially the nitrate in the sandy aquifer settings. They're in some locations much higher than the drinking water standards. And also towards Lake Huron in the till system too, with the tile drains, we are seeing some quite high concentrations, up to like 40 milligrams per liter of nitrogen in the shallow groundwater. So there is definitely an impact.
Oh, question over here at the front. Oh, please wait for a mic because people online won't be able to hear.
I also did my research on agricultural tile drains and end-of-pipe treatment systems with permeable reactive barriers. But more broadly speaking, it's important to know where there are or aren't tile drains when, you know, consultants are doing projects or people doing work in the area, or even counties are repairing bridges and accidentally cut into them. Is there a database online of where are all the tile drained fields in Ontario? And if there isn't, do you think it would be valuable to have such a thing? If there already is an MECP well record database, could there be a tile drain database?
Great question. I know for some sites that we've been working at, it's been very difficult to understand where the tile drains are, just because they weren't, we know that they're there, but they weren't mapped when they were installed. So OMAFA has that tile drain information. So I think it is very important, as we're trying to understand the nutrient dynamics, that we can better figure out where they are. I know a colleague of mine was using a drone to help us to try to delineate where the tile drains were in unknown areas, and we had some limited success with that. But I think we do need to have that information, and through OMAFA in Ontario, there's some available.
For those of you who don't know me, I'm Jana Ivey. I'm the Director of Water Resources for the Grand River Conservation Authority. So my area of that work is more around the groundwater program, the surface water quality program, the wastewater optimization program, which I'll talk about a little later on, drinking water source protection, and conservation services, which are the boots on the ground stewardship programs that we run to deliver cost share grants to farmers from municipalities and other sources to improve water quality, and as well as some collaborative water management planning that I'm going to talk about. But what I'd really like to do is share a bit of a different perspective. So I'm going to talk more about watershed scale, and hopefully this isn't blasphemy at a geoscience forum, but I'm going to talk a little bit about groundwater and surface water, because particularly when it comes to nutrients and nitrate in particular, you can't separate those two issues in our watershed and meaningfully talk about their impacts on our communities, in particular on our municipal drinking water systems and our wastewater treatment plants and stormwater management systems. So I'm firmly wearing the practitioner hat here, which is maybe a bit of a different perspective as well. So you've heard a little bit about the Grand River watershed here. And so you're sitting in it. I have to look up this way because I'm too short to look down there, but if you can't really see, but right around the center part of the watershed there is the region of Waterloo, and we're sitting now. So the Grand River watershed extends up, if you've been to Luther Marsh before, in Grey and Dufferin counties at the top of the watershed, and flows through much of Wellington County, Waterloo region, Brant County, Brantford, Oxford, Hamilton, Haldimand, and of course, Six Nations and the Mississaugas of the Credit Reserves are in our watershed. And there are a few things you kind of need to know about the watershed to understand the perspective around nutrients, and that's that it's complicated. But nutrient issues, be it phosphorus, ammonia, or nitrate, have driven a lot of some of the water management strategies we use to manage the system in the Grand really over the last 90 years. But the watershed is largely agricultural in land use, a population of about 1 million people and growing. And then I'm glad I put this map up here because unlike everyone else, I have a map with a lot of dots on it. But these dots are important when you're looking at nutrients. So the triangles on those on that map are the wastewater treatment plants that discharge treated effluent into the Grand River, its tributaries, right? So point sources of nutrients, not necessarily the driving source of nutrients across the watershed, except more of a source in low water times. But you have that agricultural landscape, which is a huge source of non-point source of nutrients to the watershed. And so you have a lot of sources, but you also have a lot of reliance on the surface water and the groundwater in the watershed. So not only do we have those 30 wastewater treatment plants, but we have those bluey green circles near the bottom of the map, and those are drinking water intakes. So you may know that the city of Brantford and Six Nations, their drinking water plants are exclusively sourced from the Grand River, but the region of Waterloo also takes water from the Grand River, and Guelph has an aquifer recharge system drawing on the Aramosa River as well. So surface water remains an important source of municipal supply in our watershed, despite the heavy reliance on groundwater. But even on the groundwater side, we have nutrient-related issues. So phosphorus is not a huge deal from a water supply standpoint, but nitrates certainly are. So those, that's coming up on a next map, but those yellow dots there are all the municipal drinking water wells throughout our watershed. So we have this really interconnected system of reliance on both groundwater and surface water, not just for water supply, but also for assimilation of treated effluents from wastewater treatment plants, as well as the nutrients coming off of agricultural lands. So there are a number of systems that I'll show you on the upcoming maps, municipal drinking water system, that have been identified as having I'll say a capital I issue under the Clean Water Act for nitrates or chlorides or sodium. So those are areas where either the levels are already approaching or will approach at some point in the planning horizon, concentrations meaningful from a water supply standpoint. So I'm going to talk a little bit about what the GRCA's roles are in addressing this, but I wanted to throw these maps up here because they represent some of the main sources of information at a conservation authority we have access to. So in our conservation authority, we don't have access to sophisticated models and some of the density of data that you often can find in an academic environment. So often when we're trying to step back and understand nutrient dynamics at the watershed scale, we're using data that kind of looks like this. So the GRCA partners with the province to deliver its provincial groundwater monitoring network. And what you see on the right-hand side there in those green circles are the locations of our PGMN monitoring wells. And that map is showing you nitrate concentrations. And so green is good, darker green is great. And you can see a lot of green there. If you're looking at that provincial monitoring network, those wells cited to be reflective of ambient groundwater conditions, you'd be thinking, all right, we're looking pretty good. I mean, yes, there are some up arrows on a couple of those circles, but not too bad. Except that monitoring network kind of misses the point and some real important regional considerations, and those are those purple dots. So those purple dots are the municipal water supply wells that have identified nitrate issues. So, you know, this is the kind of challenge sometimes we face in using the data that we have to try to illustrate some of the challenges that we have in the watershed. And that's where some of the work that some of you do to try to scale up learning and understandings from edge of field scale up to reach scale up to subwatershed and greater scales, that's the kind of knowledge we need to better understand nutrient source areas and how to tackle some of these issues. Similar kind of situation on the left-hand side, that's chloride there. The provincial groundwater monitoring network, those well locations are not well suited to tell the story about chloride, and those purple dots are also municipal wells with chloride issues. So bear with me if I show you a little bit of surface water quality, but just to say, knowing that the watershed is largely agricultural and we have those 30 wastewater treatment plants, you can see on the left-hand side, we have I highlighted in green and orange those basins that have higher concentrations of total phosphorus. So the more orange, the more phosphorus. And on the middle image there, you see what that same scale looks like if you're looking at individual surface water quality monitoring sites. And when you kind of line up all the maps, you get a sense of a complicated picture influenced not just by agricultural runoff from non-point source areas, but also the locations of various wastewater treatment plants. And then on the right-hand side there, for those of you interested in chloride, again, stepping back and looking at the big systems, you don't see much, but when you're looking at those urban areas, you can see those higher chloride levels. So where the GRCA comes in addition to a little bit of monitoring through those provincial monitoring networks and some other programs that we run, trying to step back and assess regional and watershed conditions and share that with our watershed municipalities and others. We get involved in a couple other points through this process. So, and one is non-regulatory programs to support pollution prevention. So many of you may have heard of the Rural Water Quality Program, which is a decades-long program to deliver cost-share grants to farmers to help keep sediment and nutrients on the landscape and out of the waterways. And the GRCA also works directly with wastewater treatment plant operators to help them go above and beyond their ECA requirements and produce excellent quality treated effluent to the Grand River to try to protect the assimilative capacity of the river. And where some of this starts to get interconnected is when you start to see elevated levels of nitrate in the Grand River, that's of great concern to those municipalities who are reliant on the Grand for a drinking water source and do not have the treatment technology to remove the nitrate, which is the case for most of the communities reliant on the Grand River. And when that starts to happen, then people start to look for the sources. And one of the sources, not the biggest source, but one of the sources are wastewater treatment plant. And that's when the pressure starts to come in to further regulate wastewater treatment plant discharges for nitrate, because most of the plants in the watershed don't have a nitrate limit on their ECA. So municipalities will get squeezed on both sides as they wrestle with this issue, either on the water treatment side to take out that nitrate, for instance, or on the wastewater treatment side for the same reason. So these problems are interconnected. And one of the ways we try to help advance this, addressing this challenge is through collaborative planning and networking. So, Dustin's presentation this morning and others highlighted no one agency, be it a provincial or a federal agency, the researchers, municipalities, or the conservation authorities, have all the tools in the toolkit you need to actually greatly make a difference in reducing nutrient concentrations or loads in these watersheds. But collectively together, we have a forum through the Grand River Water Management Plan to talk about shared management actions and start to align our actions. So that's what the Water Management Plan does, kind of lines up with municipal master planning at the water supply, wastewater and stormwater level. So We will be working with some of the folks in this room on updating that plan and in collaboratively discussing options to address high phosphorus levels through the Lake Erie Action Plan work that we do with the provincial or federal governments, or some of the nitrate issues that are going to challenge us and communities on the wastewater and water supply side. So maybe I'll stop there.
Thanks, Don, for the invitation to be on the panel. So I'm a professor at Western University and the Canada Research Chair in Water Quality. And today I'm just going to provide you an overview of some of the work that we've done over about the last 10 years in my group. A lot of the work has been, I would say, funded or supported by Ministry of the Environment, Conservation of Parks, in order to look at trying to address some of the eutrophication challenges in the Great Lakes. And in particular, phosphorus, and trying to understand how important is groundwater as a pathway in delivering phosphorus into surface waters, so into the tributaries and directly into the lakes. So I just have a couple of slides, but we've done a couple of different projects. One of them was a large project that we did, and this was done in collaboration with Jim Roy at Environment Climate Change Canada, as well as Adam Yates at the University of Waterloo. And in this particular study, we were really trying to understand what are the controls on hot spots and hot moments of groundwater phosphorus inputs into agricultural streams. So what I mean by that is where is groundwater an important pathway delivering phosphorus into the streams, and where is it not? And so this can basically allow us to better prioritize management as well as monitoring plans. And then in addition to understanding the hot spots, we wanted to understand the hot moments. So are there certain periods of time, certain seasons, maybe it's the spring conditions when you've got higher water tables, or maybe it's after storm events. Are there hot moments or hot times where we see disproportionately high inputs of phosphorus into the streams from the groundwater pathway? So for this particular project, we were working at multiple scales. We had some work that was done at the watershed scale. Here we weren't doing groundwater sampling, but instead we were doing stream sampling along stream networks to use traces for groundwater discharge, so in particular radon, where we could find stream reaches where we had groundwater gaining and losing streams, and then try and correlate that to what the phosphorus and the nitrogen concentrations were in those streams, to see under base flow conditions, was groundwater a control on the phosphorus levels or nutrient levels down the stream network. Moving from the larger scale, we also did work in riparian zones. So many of you may be familiar with riparian zones, which are a really good best management practice for trapping or retaining the phosphorus that's moving from an agricultural field and limiting its inputs into the stream. The real challenge with phosphorus is that when you trap phosphorus, it's great, but this is really just a temporary storage, and that there can be certain periods of time where that phosphorus gets re-released and you end up getting a hot moment of phosphorus inputs through the groundwater into the stream. So this is what we were looking at with the work that we did on riparian zones. We then moved from that scale down to the smaller reach scale, looking at the looking at groundwater surface water interactions and the patchiness and how spatially and temporally variable the phosphorus inputs are across a stream bed in an agricultural area. And looking at what the controls were on where we saw high phosphorus fluxes across that groundwater stream interface and where we didn't. And this was really nice because, as I said, we were working with Adam Yates at the University of Waterloo, and we were also linking this patchiness in the groundwater phosphorus inputs into the stream to the algal abundance and community in the stream as well. So moving from kind of the stream environments, we've also done a lot of work in my group looking at direct groundwater discharge and how important this pathway may be in directly delivering phosphorus into the Great Lakes. So there's many different sources of phosphorus in the nearshore areas. You know, one might be that we've got a lot of coastal communities that use septic systems, but we also have a lot of large urban areas where, for instance, we could have leaky sewers that are contributing nutrients into the groundwater. So we've done work trying to understand, I don't know how to go back there, trying to understand that pathway from the groundwater into the lake. And in particular, when you might have a really high phosphorus plume that's moving towards the lake. For instance, this is some work that we did where we had a septic system. We were tracking an individual nutrient plume from a septic system moving into the lake. But we've got high phosphorus in the groundwater, much, much higher than what's in the lake. But what's really complicated when we're looking at groundwater surface water exchange is that we get a reaction zone that occurs right at that groundwater surface water interface that can trap the phosphorus and ultimately trap it and prevent its release into the surface water, but only temporarily. So then are there certain periods of time where that phosphorus could then be released into the lake. So we've done work looking at individual plumes and understanding what that reaction zone is, what it looks like, what the controls are on it. And then we've also done some larger scale modelling work that was based on field data from Jim Roy, where we were looking at kind of the legacy effects of phosphorus inputs. So this particular study was up in Wasaga Bay, where they have decommissioned septic systems. So septic systems that are no longer, they now have a wastewater treatment plant. These are old decommissioned septic systems, but we're able to show how these septic systems, because phosphorus moves so slowly in the groundwater because of slow groundwater flow, but also because of phosphorus retardation or absorption, precipitation in the groundwater system, is going to take decades or hundreds of years until the phosphorus from these systems are discharged fully into the lake. So this work here just is one of the examples of kind of highlighting the legacy effects of phosphorus. So some of the overall kind of takeaways from this work is that phosphorus is so very, very complicated. So it's governed by so many different multiple biogeochemical processes. You might trap the phosphorus in different zones of the aquifer, but it can later be re-released. You've got that zone of high reactivity near the groundwater surface water interface, which means, and that ultimately controls what discharges from the groundwater into the surface water body. And then finally with phosphorus, it's really challenging you might see really high phosphorus concentrations in the groundwater or in the stream bed discharging into the stream, but you've got to be able to untangle what is associated with human activities and what is just naturally occurring phosphorus that's there because organic matter has mineralized. So this is where phosphorus can get really challenging to understand. And then just caution about using kind of snapshot one-off groundwater sampling events to understand, concentrations of phosphorus in the groundwater. Be careful using groundwater wells that aren't really close to the stream. So even if they're 10 metres away, that might not necessarily be the concentrations of phosphorus in the groundwater that's discharging. And then finally, just a reminder about these long legacy timescales for phosphorus to reach surface waters, which is so very, very important from a management and a policy perspective. And then I'd just like there's a lot of people who contributed to the work. I flipped over the slide. I don't know how to go back, but there we go. So thank you.
Thank you, and thank you all for staying till the last set of slides. I wanted to give a brief overview of some of the research findings in our group, kind of around this node. And this is a good point to be talking to because you've all heard multiple speakers speak about the groundwater-surface water interactions, which is one of my starting points in groundwater-dominated room. So one of the things that I wanted to share with you to start is the results of one of our work. We work a lot from across scales, but from watershed to regional scale. So in this work, we looked across 400 watersheds in the Great Lakes Basin. And one of the key things that we found in there is that dissolved phosphorus concentrations are increasing in 83% of the streams that we are looking at. Now, that was really concerning because algal blooms, dissolved phosphorus, are much more relevant to algal blooms than particulate phosphorus because they are more bioavailable. So that's what the percentage of watersheds showing an increase in dissolved phosphorus. And it's not just phosphorus. So this is a 2016 paper by Kathy Eimers and others that also showed evidence of nitrate increasing across this region. And then this is a study that was done. It's called the multi-watershed nutrient study, which some of you might know, where they had these controlled set of watersheds that they sampled and modeled in the 1980s, and they went back to those watersheds. And one of the main findings that I want to point your attention to, a lot of times when we look at nutrient loads increasing, we blame it on climate change, meaning flows are increasing, it's becoming wetter in some regions, so that's why. But what they found is that, yes, flows are increasing, but nutrients are increasing at a faster rate than flow increase can tell you. So flow is telling you part of the story, but it's not telling you all of the story. And why am I talking about this in a groundwater conference where part of it is the reason they are increasing is below the surface. It's not on the surface, right? So it's the subsurface contribution that is creating that kind of an increase. And the other is, though this data set doesn't tell you anything about groundwater nitrate concentrations, other work we are doing in some other areas show that groundwater nitrate concentrations are also increasing. So what is going on? Because if you think about these landscapes, if you think about the last 10 or 15 years, land use has changed, but not dramatically. So you cannot really blame it all on the land use change that these concentrations are increasing. So why are these concentrations increasing? And as you heard Jana talking about this increase in concentration is a real-life challenge in terms of management when that happens. And where are they increasing and where they are not increasing? Dissolved phosphorus might be increasing in some locations and nitrate might be increasing in some other locations. How do we understand that and how do we manage that? So I'm going to give you a little bit of our conceptual understanding or rationale why that is increasing. And that has to do with climate change, but in a little bit of a different way. So what happens, a lot of our previous work has focused on this idea that you also heard Clare talk about, legacy nutrients. So legacy nutrients, legacy nitrogen, phosphorus, are there in the top few centimeters of agricultural soils they have built up over decades. Now, generally, they are immobile, so it's fine. But if you have more contributions from the subsurface pathways, they can be activated. So our hypothesis is what is happening is our winters are getting more temperamental, right? So they are getting warmer, but more importantly, you get very warm days and you have these runoff events followed by freezing days. So what happens when you have that is when you have those warming up during some of the days, your subsurface pathways and your tile pathways are activated, and you get this flush of nutrients in the stream. And it is happening, as you heard one of the former speakers say, it is happening during the non-growing season when the crops are not on the field, when there is nothing growing in your stream, so it is there, and it's sitting there, and it's going to your lake, and whenever the temperature gets a little bit warmer, the nutrients are right there to promote the blooms. Right? So the main idea over here is the winter temperatures are creating these increasing melt events that's increasing these pathways through which nutrients come into the waters. When you had more frozen winters, what you would be seeing is most of the runoff would be coming in like April, May. And when you have that, you have a lot more surface pathways activated. Surface pathways bring in particulate contaminants. Subsurface pathways bring in more dissolved contaminants. More subsurface pathways are being activated. More the subsurface needs to understand, like the understanding of the subsurface in these surface water problems is really, really critical. What we found, I'm not going to show you. So we built a whole range of machine learning models to understand what drives these patterns. And the key thing that we found, which was not what I was expecting the usual culprits, agriculture and all of that, but what we found is that these increases are greater at higher latitude, where you are getting more that temperature-driven effect. Whereas, so within the Great Lakes Basin, as you go further north, where you're getting more of these increasing winter temperatures, you're getting more of that effect. That was the only driver. So while, of course, agriculture and nutrient inputs are, current inputs are driven by agriculture, but this increase that we are seeing might be that it is a climate-driven impact. Okay. So we've also done some modeling to kind of prove those hypotheses. So to solve a problem, we have to first identify it. So monitoring and modeling is a key part of this. So building off this, one of the things that our group has been working on is this portal that we've been working on called Poseidon. It's called AI for Water Quality. So the idea of this portal is, if you go on here, you can look at all the inputs that are coming to the waterway. So we map out fertilizer inputs, livestock manure at a 250-meter grid scale. So you have your watershed, you can go clip that watershed, and you can figure out what the inputs are. If you're doing modeling, it can be useful to you. If you're doing more watershed report cards, it can be useful to you. We also build, using monitoring data, we build machine learning models that can stitch between those data sets, and you can also download the results of those machine learning models. This is still under construction, but it is alive to be able to view. If anybody is interested to participate, there's a subgroup of people also in this room, GRCA and others, that are a part of our advisory team. We are looking to build this portal with help of people to tell us what would be valuable. Right now, it's only for surface water. Aspirationally, we would like to build it both for surface water and groundwater systems. So now, that's the diagnosing of the problem. I also wanted to talk briefly about diagnosing a problem is not going to solve it. How do we solve these nutrient pollution problems in our landscapes where there is a lot of agriculture, which is not going to go away, population is increasing, that's not going to go away. So how do we solve this problem? So in this project, we are looking at these three groups of solutions. I will talk briefly about each one of them. So the sustainable farming, the idea of sustainable farming is, if legacy nutrients, legacy phosphorus has built in our soils, can we apply less fertilizer and get the similar crop yield? And the answer to that is yes. There's multiple studies that have shown that's possible. The reality of it is more complex because it's tied up in farm insurance patterns and policy metrics. So I'm going to jump over that and talk a little bit about wetlands. So we all know wetlands are good. They retain nutrients and improve our downstream water quality. But when we are thinking about restoring wetlands, there's a whole range of questions that we don't have a good handle on. Which wetlands to restore? Where in the landscape? Where would they have the greatest impact? Some of our work show that all wetlands are not the same. So small wetlands are actually much better at retaining nutrients than large wetlands, and I can tell you the reason why if anybody is interested. But bottom line, 10 1-hectare wetlands remove more nutrients than 1 10-hectare wetlands. And yet, if you think about how land use proceeds, we lose the smaller wetlands, and sometimes we lose a few of them, and we want to replace them by a large wetland. So that's a problem. In this work, what we are doing, and this is based on something we've also done across US, is building these large-scale models to say how many wetlands to restore and where in the landscape, and where can we restore them with less impact on the farm economics. That's the biggest question. The other thing that we found is, so we built models. This is a model for the Grand River watershed that we built that takes into account nutrient legacies. And one of our key takeaways from the model was that livestock manure is the key. If you can get a handle of managing livestock manure, you get a much greater return on investment in terms of water quality and nutrient pollution. But that's not an easy problem. It is a distributed problem. One of the problems with that problem is we don't know where a lot of the livestock operations are at a large scale. We can figure out livestock numbers at county scale, but if you want to go finer than that, there's a whole range of reasons that data is not available to us. So what we did was we used remote sensing to identify every livestock barn across Ontario. And then using that, we built, this is not the best, we built a spatial optimization model. This is a completely hypothetical scenario where we are asking if we wanted to build biodigesters in the landscape to take these manure and get energy out of it, how many digesters, where in the landscape, what are trade-offs? And there's already current anaerobic biodigesters in the landscape, a lot of it for the wastewater treatment plant, some of it for farm digestion. One of the biggest challenges is your operation has to be big enough for a digester to be feasible. So in this case, we are trying to think about if you clustered them together and if you added food waste, how can you manage effectively the waste at a large scale to be able to address these problems? Thank you for your time, and with that, again, I am going to, oh, sorry, I was going the other way. Thank you for your time.
All right, so why do 10 1-hectare wetlands do better than one 10-hectare wetland?
Thank you for giving me more time to speak. The reason is most of the action in a wetland where, say, for example, nitrogen removal happens at the sediment-water interface. Like you heard Dr. Robinson talk about those redox, they are very redox active. So if you just do geometry, a small puddle has more surface area to water amount, and a large puddle has less surface area, the reactive area to water volume. So that's why a small one works better than a larger one.
So follow-up question to that. In terms of policy, you may be aware that recent changes have dictated that wetlands can't be complexed like they were before. And smaller wetlands aren't provincially significant. So what we're seeing, as someone who reviews land development applications, not necessarily from a wetland perspective anymore, but we see the smaller wetlands, they're saying, oh, this is just a small wetland, and they're removing them from the landscape. Is there any chance to get some of this knowledge into the hands of the policy people to look at the significance of some of these smaller wetlands that may serve multiple functions on the landscape?
Yeah, absolutely. I think when we first did this work, which is in 2013 or 2014, I had gone and talked to some of the CAs who, even in those times, they were struggling with the fact that the small wetlands, it's easy to pave over them. And it's really hard to argue for their value.
And we spend a lot of time saying, okay, well, you can obliterate that one, and you'll compensate by building a bigger one over here.
Exactly.
And that's exactly what we...
If I may add one other thing to bigger one, sometimes we also say we can compensate it by building a one in a more natural area, right? Which are not seeing the nutrient inputs. So it's even taking it a step further and building a nice natural wetland in the Algonquin, but it's not solving the nutrient problem that Lake Erie is facing.
I'm not sure if I heard this address. Maybe if I did, I'm tired. From a nutrient perspective, the role of tile drains, can someone address that? You know, does it move the nutrients more quickly to the streams and so on? And is that what we don't want to have happen? I'm just curious and my question comes from, I understand that farmers can install tile drains without permits. And this happens everywhere. And they can dry up some of these small 1-acre wetlands without a permit. And when you talk about managing, you know, from a watershed perspective, I understand, you know, agriculture is something we can't touch, but it feels like it's causing some harm, unmitigated harm.
I mean, I would say Jana would probably be the best. She's the one who I would say has done the most on tile drains. But yeah, I mean, when you have tile drains, you're basically creating short-circuiting pathways for those nutrients to reach a surface water body. I mean, obviously they have other important benefits they provide, but yeah, a lot of studies that look at the subsurface transport of the nutrients in the agricultural fields, you know, tile drains are a major player in those phosphorus exports to the surface waters.
Maybe I would just add, you know, I think as an organization that delivers programs to get money into farmers' hands to to do projects on their land to protect water quality, I think it's important to think about the farmer's perspective, right? In a sector that is already pretty heavily regulated, if you are in compliance with the Nutrient Management Act, you are, managing your lands for sustainability in a very tight economic market. I think that the question is not should farmers be allowed to install tile drainage without a permit, but how do we support farmers to make decisions that are protective of the broader watershed? And I think many feel that they are already doing that, and clearly we can see from the nutrient levels in our waterways and groundwaters that it's not enough. But what kind of support would be needed to achieve that next level? And knowing that the complexity of the legacy issues, we struggle even to quantify the benefit of the extensive number of best practices farmers already have implemented. So it's just like the technical science side of it, on the governance management side, it is equally complicated, and no one silver bullet.
Thank you very much for each of the presentations. I'm wondering, I think I only saw the soluble reactive phosphorus being considered. I wonder if any of your research or monitoring, you're taking into account the removal of phosphorus through like crops or other reacted phosphorus. I'm just wondering if that's part of the legacy phosphorus that's considered.
Yes, absolutely. So what happens with phosphorus is that what you apply as fertilizer, quite a bit of it, so when we do our nutrient budget, we account for how much crops take up. And then the rest of it is the remaining in the soil. Some of it stays in the soil. A small fraction of it shows up as dissolved phosphorus in our streams. But a lot of it stays in soil. So yes, when we are doing the nutrient budgets on the land, the uptake by crops is a part of that budget, and every crop has different uptake coefficients, so we consider all of that in our budgeting.
Sorry, if I could have just a follow-up question.
Yes.
For Clare. I just wondered, you spoke about not making policies without considering the long-term lag consideration. I would suspect that's because of the bound up phosphorus, I suspect, but I just wondered if you're considering that, if there was a way of harvesting phosphorus that's been taken up.
So that is one of the things that I quickly went over, and the answer to that is yes. I mean, there's a really nice case study around here where if you apply less, then the crops start taking up what's the legacy phosphorus in the soil, right? And that's the way of harvesting it. So a lot of times when people have done field trials or larger scale trials, it's always there that you reduce the amount of fertilizer application and your crop production does not go down, sometimes for 5 years, sometimes for 7 years, and that's when it's harvesting that legacy phosphorus. The challenge in doing that at scale is that every farmer's field is different. So you would have to test and monitor and have insurance mechanisms to say if the crop production goes down, then would they get compensated for it? So that's where it's not easy to do at scale, but there is legacy in the soil that could be harvested effectively. What has eroded and shown up in our stream beds is gone. It's the horse that has left the burn, but what is there in the soil, it can be harvested absolutely.
Yeah, and my comment around the legacy is the fact that, like if a management change is made and you put in best management practices, it's just more that we have to be patient, that it takes time for these solutions to work. And we're talking about, tens of years so for instance, if you decommission, you might have a coastal community, you think that that's a major contributor of phosphorus into a nearby tributary. You decommission the septic systems, but it's not like you've solved the problem straight away. It takes time for whenever you're talking, whether it's phosphorus or any groundwater contaminant, it takes time because of those slow groundwater flows for the contaminant to kind of move out to the surface water body. And it's just made worse by phosphorus because it has that high tendency to bind up to sediment and then later be released.
So this question's for you, Dr. Robinson. So about one of your plots, the reach scale plot, where you're showing the more and less reducing conditions and how there's higher concentration of SRP, which I know is soluble reactive phosphorus.
Yeah,
Thank you for explaining that. I knew it was reactive phosphorus. I didn't know the S. So one thing for me when I see that more or less reducing conditions, I think, well, there has to be more electron donor that's controlling that redox conditions. And so if you have higher organic matter or like SOM, that also correlates to low, there's an anti-correlation to hydraulic conductivity there often, where you have finer grain materials with more organic material that's acting as electron donor that's promoting these reducing conditions. And so what I've found through work I've done too is, yes, there's, how do you deal with the fact that you want groundwater to be, we think groundwater is very important, groundwater surface water interaction is an important aspect. But in these areas where you have really strong reducing conditions, you also often have very low hydraulic conductivity, and so is it really contributing much to the stream? And so have you kind of delved into that aspect in your research?
We've thought about it a lot. We don't have an answer, but it's exactly right. Where you tend to have reducing, where you tend to have higher phosphorus concentrations, where you have reducing conditions. Where we see the reducing conditions, it's often in tighter. It can often be in tighter soils, or you've got higher organic matter there. Whereas when you've got sands and gravels, you might have more groundwater surface water exchange happening, but it's more oxic, you've got lower phosphorus concentrations. So in the work that we did, we found that it probably was more the tighter soils. We have lower like water fluxes, but we had, the concentrations of soluble reactive phosphorus there were, 1,000 times higher than the surface water. So even though the water fluxes were low, that was probably the area where we had the higher, where groundwater was a more important contributor. But what was really challenging was that the soluble reactive phosphorus was really high just because of organic matter mineralization. So is that just naturally occurring, or is that linked to the nearby agricultural field? So it's very challenging to really kind of understand where you expect to see these hot moments, because it's so complicated between the physical processes, the geochemical processes, just naturally occurring phosphorus versus the kind of anthropogenic phosphorus associated with the human activities.
Yeah, and just like a follow-up to that. So when you're trying to then scale that to an entire watershed, and you have maybe these little hot spots that are very small scale,
Yeah.
This is where groundwater surface water interaction becomes challenging, how to scale it up to an entire watershed. But so do you find that there are are there hydrogeologic settings in riparian zones or wherever where you still have permeability, like significant hydraulic conductivity, maybe a silty sand, but there's dissolved organic carbon pockets that act as enough electron donors to still be, producing, there's still a lot of groundwater contributed to the stream, but there's also enough electron donors where there's reactivity happening and reduction happening? Like, is there kind of an optimal setting for this?
Yeah, I don't have an. It's so site specific, and that's what we took away. Like, it's really challenging to kind of generalize it. So, unfortunately, I don't have an answer yet about where do you see these hotspots and how can we make these predictions of where it's higher, because it is really complicated, even just looking at a single riparian zone. We did find, from the large kind of network stream longitudinal surveys we did find pretty good relationships between when we had a groundwater gaining stream and where we saw changes in like the nitrate levels in the stream. So nitrogen's a little bit simpler than the phosphorus. And so we were able to see, we've got this groundwater gaining stream, the groundwater nitrate concentrations are high around this stream reach. So we're actually seeing this high nitrate in the stream during base flow conditions linked to the groundwater. But with phosphorus, we saw nothing. Like, it's too complicated by the processes that are happening at the groundwater surface water interface, but also just the processes occurring within the stream itself, like the biological uptake, the organic matter mineralization, etc. So we really saw no relationships between the groundwater traces and the phosphorus. Yeah.
Thank you.
Hello, I think this question is for Dr. Basu. I wanted to ask about the use of methanotropic bacteria to offset phosphorus. If you've looked into environments where it might be feasible, I know that it's a very complex, site-specific, but I'm wondering if you've looked into that.
No, not methanotrophs. I mean, there are multiple that kind of falls in the space of bioremediation, right? And one of the challenges with these kinds of non-point source pollution problems is how to do it at scale, right? So if you have to do any kind of augmentation or anything in these systems, how do you do it at scale? I've seen examples of people that have done, I think for nitrate pollution, permeable reactive barriers that are larger, but the challenge is that, I think.
I have a very general question. Are there programs to help farmers estimate the right amount of fertilizers that they should apply?
Yeah, I mean, go ahead.
I mean, yes, I think within the province, precision agriculture has gained a real focus to provide farmers with the tools to customize kind of that 4R approach to applying nutrients to the landscape. So the tools exist. I think the missing piece is application of those tools, right? They take time, they take energy, they take resources, they take willingness. So that's not a solution you impose on a private landowner. It's one that they seek out if they see value in it. So, you know, there are tools out there for sure. There are those too. Most incentive programs are a cost share, right? So when economic times are challenging for the agricultural sector, which is almost all the time, you still have to have your half of the grant to bring it forward. So, you know, there are a lot of active programs and a lot of focus on Lake Erie right now. The Canada Water Agency and the Ministry of the Environment in the last year released an evaluation report on how the first 5 years of implementation of the Lake Erie Action Plan has gone, and you know, they've looked at the data and basically concluded that they can't discern a reduction in phosphorus loading from the tributaries to Lake Erie. There's so much climatic variability, it's so complicated, and so their way forward is to stay the course and to continue investment in voluntary cost share programs at as great a scale and with as much precision targeting as they can, but it's still a voluntary process. So I think it'll be interesting to see in that next 5-year cycle whether that enhanced implementation moved the needle or not.
This is a sort of a follow-up to Dr. Rivard. It seems to me, if I was going to summarize, the solution is with the farmers and they need to be incentivized in some way, you know, either financially or but given help. And this is a question to all of you. Would you agree with that, yes or no?
I agree. I think it's in the Grand Watershed anyway. Phosphorus and nitrate, kind of two driving issues for different reasons, are largely non-point source issues. And the land is in agricultural production, so you are working with those private landowners. And this is not a problem that's going to be regulated away. So voluntary programs, cost share programs are where we need to go. The question is, you know, what is required to actually move the needle? And I think the biggest challenging, and you know, when you look at some of the great research being done on the legacy, you know, we don't live in a political climate where provincial and federal investment in cost share dollars are going to want to wait 40 years to see the benefit. How is a municipality going to plan their long-term water supply not knowing how much you know, those nutrient levels in those supplies are going to change over 40 years? That's a tall order. So I think it's the right solution, but that doesn't tell us how to make it successful. I think that's a challenge.
I think if I may, one of the things that I feel like in that space, and part of it, because it's a non-point source and a solution that's so behavior driven, the fertilizer application, it's a hard one to make. I think, but as scientists, academics, I think it also falls upon us to figure out solutions that are economically feasible. So somebody asked the question about tile drains. One way farmers use tile drains is the low spot in their farm field is what they drain at the last, and that brings in a huge amount of nutrients if there are incentives for those low spots. But also, instead of thinking just about reducing fertilizer application, which my personal feeling is it's a much harder problem to solve because of margin of safety, right? Even if they applied less, if there was a poorer crop yield, it's hard for them to get insurance. So it's a really tough problem. However, livestock manure, I think, is an easier problem. Because a lot of times when we drive around, we can smell it in winter. So there are nutrient management plans, but they're hard to implement on an individual basis. And there's a lot of livestock operators of different sizes. But it is something that could be maybe centralized. We learned how to treat human waste. Can't we learn how to treat livestock waste effectively? And this is where the conversation related to digesters, again, digesters can be a bad thing if they pollute the environment, but if they are done with the proper regulations. So this is where I hold half a science hat and half an engineering hat. And part of me thinks that voluntary cost-sharing behavior change is good, but can only take us so far. So if it's a problem related to some kind of source, we had human waste, we solved it. It's still not solved in some parts of the world, but in the Western world, we solved it. Is there a way to solve the problem in a less distributed and more centralized way? Is there money to be made out of it? So digester can potentially make money. And if you intersect the water sector with the energy sector, with the kinds of RNG pricing and incentives that are there, can you start addressing that problem?
I was just going to follow up on that. So you might tell from my accent I'm from the UK. I'm no longer in touch with what's happening in the UK anymore, but the nitrate problem there is horrendous, and it's been there for a long time. And the only success that they ever had with actually reducing nitrates was actually paying the farmers, and that's called the Nitrate Sensitive Area Scheme. Direct regulation, the nitrate vulnerable zones, which were done through the Groundwater Directive, part of the Water Framework Directive for the UK, hopeless failure. Hopeless failure. You've got to incentivize it, and then something might happen. That's the UK experience when I left in 2010.
So one of the questions I have is, have you guys, you might have looked into this, but the idea of taking like really large agricultural plots and segregating them into smaller chunks, and then going from more, the monoculture to the organic. What is the feasibility of something like that? And yeah, I'm just curious about your guys' thoughts on doing something like that, because I think farmers who own these large plots of land are going to be very reluctant to strictly move from mono to organic. But if there's some kind of a, like a staging phase where they start doing smaller plots, what's the feasibility of something like that?
Okay, I will attempt. There is a very large-scale study done on organic agriculture. And one of the main, I don't remember the exact details, but one of the main findings of the study is that one of the perceptions that we have that it would solve our problems is not necessarily correct, right? Because it also requires input. Crops to grow need inputs, right? So yes, you're right. Thinking about, but there are solutions. Like you could do more natural vegetation and intersperse them in agricultural land. You could put small wetlands in farm fields. I was actually at a meeting where I had a really interesting conversation, and this is true in Ontario. There's some case studies where if you take some parts of the farm field, not the entire, pockets that are low yielding, and convert them to wetlands or something else, your net farm profit increases because those plots actually have poorer crop growth. Again, a lot of these solutions do exist, but how do you do it at scale is the bigger problem.
As we wind up, this is almost more of a comment than a question, but I'm aware from some of the research at TRCA and water sampling that at least bacteria goes up once you enter the urban framework of the GTA. Now, if nutrients are following that same pattern, is agriculture the whole problem, I guess? Or are there other solutions? Now, whether it's combined sewers, some blame it on pets. But anyway, interesting.
And maybe I could just note, and I will start by saying the GRCA doesn't sample surface water quality for E. coli, so I'm not suggesting this based on that kind of monitoring, but you know, we have this more urban central part of the watershed surrounded by a lot of agricultural lands, and we do know that that urban developing area does have a signature from a you know, certainly from a sediment dynamic standpoint in the watershed, and we probably don't have a great way of characterizing that yet, although some of the municipalities are developing and implementing increasingly sophisticated monitoring programs, and I think as you know, the province moves forward with its consolidated linear infrastructure monitoring requirements, we may have better ways to characterize the urban non-point source contribution moving forward.
Thank you. Given the fact we're 15 minutes, oh,
That's fine.
oh,
I
sorry.
was just going to say, we've done quite a lot of stormwater monitoring in London for soluble reactive phosphorus and total phosphorus. And definitely, I mean, urban areas are important and potentially overlooked contributors. And whether it's from like developing areas where you've got, you know, suspended solids that are coming off, they've got phosphorus associated with them, the particulate phosphorus, you know, people putting fertilizers on their lawns, the animal waste, etc. But and even like we see in the spring with all the leaf litter decay, etc. People putting their leaves out on the streets, the bags aren't properly closed. You do get high phosphorus runoff from the urban areas, and often we point to the agricultural areas, but I think we also need to reflect on what we're doing in the urban cities as well.
Thank you, Claire. Yes, given the fact we're 15 minutes over time, and at least one of our panelists has to leave urgently for a personal appointment. Anyway, I'd like to thank all our panelists. If you have some further questions, they may be able to stick around for a little bit, but I'd like to thank you on behalf of the organizing committee for being on our panel today, and for you in the audience for coming to Waterloo today, so thank you.